Hello, this is Dr. Lukes, and this is the solution to exam 3, and we're looking at question 1. So in this particular question, the first part, you were asked to use a material balance to determine the mass of steam that must be vaporized, and that's really key, vaporized in order for the product to be 25 weight % sugar. So the idea is that you're going to bring in your feed, you're going to be providing some steam that is going to condense, and that will create two phases with this heat addition. You'll have your liquid product, so L or P, and you will have a vapor, which is vaporized from this material. So this is asking for how much is V. And we have 10,000 kilograms per hour in our feed stream. This has a content of 0.15. We're looking for a content of 0.25. And as far as sugar goes, the vapor has 0% sugar. And so therefore our material balances for overall F equals L plus V, well, S plus F equals L plus V plus S, but those S's are going to cancel out. And then if I look at just the sugar content, I have 0.15 F equals 0.25 L. And so therefore L is 0.15 over 0.25 times my 10,000. And so L is 6,000 kilograms per hour. V, therefore, is 10,000 minus that, so 4,000 kilograms per hour. If you then went ahead and found S, the amount of steam, well, that was fine, but I was asking for how much steam was vaporized, not how much was condensed. In question B, you're asked to basically look at the energy balance. And so the energy is going to be for, if we're looking at just the product side, because I don't have information on the steam side, so I need to look on the product side. So the mass flow rate, and actually let me use the variables that I used up above. So F times the enthalpy coming in, L times the enthalpy of the liquid leaving, and V times the enthalpy of the vapor leaving. Now remember, our notation is lowercase h represents liquid, uppercase H represents vapor. Now if I do this based on in minus out, then I don't have to do heat of vaporization. The alternative is to follow the path. But if I do this, I need to then come up to the table of data and figure out what all of these things are. So it came in at 25 degrees C, so this is going to be my HF. The vapor space is maintained at 1 bar absolute pressure, and so therefore this represents the product materials. So this is going to be my H for my liquid, and this is going to be H for my vapor. The data down below, this would represent H for my steam in. This is H for my steam. Actually, this was in, this one was out. And this is lambda for the steam. This is lambda for my product. So if you do this, then Q is, and using these flow rates, which are not the same as you had just a moment ago, 4,000 kilograms per hour times 417.33 plus 6,000 kilograms per hour times 2674.95 minus 10,000 kilograms per hour times 104.84. We end up with roughly 1.66 we'll call it 1.67 times 10 to the 7th kilojoules per hour. I did ask for it in kilowatts, so 1 hour is 3,600 seconds. The answer, therefore, 4631 kilowatts. And the final part, I asked for, if I found Q to be 100,000 kilowatts, what's the area for this? So the formula we're asked to use, now sometimes we use delta T log mean, but they had said that for these problems, they recommended using delta T at the exit. And so therefore, delta T at the exit is my exiting streams. My V and L, that exit, they are at 99.6 degrees C. And my steam, its exit, is 250 degrees C. Now remember, this is, because I'm using U, this is the overall heat transfer, so I want overall delta T's. And therefore, A is Q over U delta T at the exits. So 100,000 kilowatts. U was given as 1.5 kilowatts per square meter degree Kelvin. And delta T is 250 minus 99.6. Remember that delta T in degrees C and delta T in Kelvin are exactly the same. And so when I do that calculation, we get roughly 443 square meters.